afternoon, and welcome everyone to the Rancho Mirage Library and Observatory. We really appreciate you being here. This day is a special day in a number of ways. It happens to be, well, a great lead-in to the holiday season, as we've been celebrating quite a bit this month, but it is also a special day as it is one of the most astronomically focused holidays. It is the winter solstice. So thank you guys for joining us here today. Now, my name is Eric McLaughlin. I'm the astronomer for the facility, and I have the pleasure of introducing our speaker today. As we get going, though, we want to remind you guys to silence your cell phones to make sure that our presenter can actually, well, go uninterrupted throughout her talk here today. Now, as we're going, I want to note a few things. A really important thing to note is the Library and Observatory Foundation. Many of our programs are funded specifically through that foundation, and our programming in general is made possible through the Rancho Mirage Library and Observatory Foundation, so a special thank you there. And a special thank you as well, of course, to our speaker who offers her time here, as well as through NASA, who encourages her to offer her time to us today. So a special thank you to the National Aeronautics and Space Administration. Now, I want to highlight a few things as we are on the winter solstice. This means we are heading towards the end of the year, and we have a couple more programs after this today that are observatory related. When we're done here, we will be doing a daytime tour of the facility, and then this evening, depending on what the weather is doing, we'll have some interesting things going on. We have from 6 to 7:30 our open night, which if we have a nice clear sky, we'll have telescopes set up, but if we don't, we'll be doing projection in the dome. We aren't expecting it to rain on us, so we aren't expecting to have to cancel. So just want to let you know on that. But these programs today will actually be the last of the programs at the Rancho Mirage Library and Observatory for the end of the year, because starting on Saturday, we will be closed down through the beginning of the next year. So if you want to keep up to date on that, please check out that program guide we've got at the back, as well as you can sign up for our e-newsletter to be kept up to date on all of those things. Now, with that said, I want to introduce our speaker with a note on what she's talking about. Now, let's rewind back to September 26, 2022. The NASA Double Asteroid Redirection Test, or DART mission, demonstrated our potential to respond to asteroid impact hazards with a successful test deflection of an asteroid. But how do we know about these near-Earth asteroids in the first place, let alone if they're headed our way? NASA's Planetary Defense Coordination Office and collaborators are on the job finding asteroids before they find us. Astronomer Dr. Kelly Fast manages the Near-Earth Object Observations Program in NASA's Planetary Defense Coordination Office at NASA's headquarters in Washington, D.C. She's a good friend of the library and observatory and one of our favorite presenters. So please join me in welcoming Dr. Kelly Fast.
Thank you, Eric. Oh, thank you so much. It's wonderful to be here again. I had the privilege to speak to this group here a couple times before the pandemic, and just enjoyed it so much. So it's wonderful to get to come back again to talk about some things that have happened that at the time I was talking about in kind of a forward-looking sense, and now we can talk about how things actually wrapped up, and then back to the subject of, how do we even find the asteroids? I grew up in Hollywood, California, out here, and so for me it's like coming home. My parents have lived in Rancho Mirage for the past couple of decades, and so this has been like a second home to me. Have enjoyed coming out here and seeing what the library has done with establishing the observatory, and then what Eric has done with the program coming on board and setting up all these activities. Even through a pandemic, I'm just so pleased everything is just in such a wonderful situation after the pandemic, and thanks to his leadership and to all of the volunteers, and I know a number of them are here. Really fantastic, and so if you haven't done so before, and it may or may not work tonight, but please take the opportunity to look through those telescopes. It is just outstanding that what you can see even out here with the city lights and everything. So I can't exactly take credit for this title, Finding Asteroids Before They Find Us. That, I think, was coined originally by Don Yeomans of the Jet Propulsion Laboratory many years ago. But then I like to add to that, and then we also want to get asteroids before they get us. And so instead of talking about the finding first, I'm going to kind of do reverse what I'd normally do and talk about getting the asteroids, because as Eric mentioned, we had a pretty significant mission event recently, and some of you I've talked to had seen it even live as it was happening. But let's take you back to kind of the roll-up of what happened with NASA's Double Asteroid Redirection Test, or DART.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss.
4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
NASA, we like to be very dramatic, but this was a very, appropriate thing to be dramatic about. It was really amazing how this all worked out. But let's break it down a little bit, because some of you, and kind of see out there, how many did kind of see this as it was happening? Did you watch the mission or follow it? So a number of you, and so, but for others, you might want to hear more about, what was this all about? And this was a demonstration of how we might deflect an asteroid if we ever found ourselves in that situation. Asteroids, they're great for studying for science, for looking at the history of the solar system, being kind of the leftovers from that. They're wonderful exploration targets for science, and maybe in the future for human exploration. But also, we just want to make sure that we're never at the same place at the same time as an asteroid. Impacts have happened on Earth through its history, and they will happen again, but we're in an amazing time now where we're empowered to find them, track them, predict if they're going to impact, and then maybe even do something about it. But the thing is, it's all physics. We can kind of calculate it all and everything, but there's nothing like trying to test something on an actual asteroid and see how it actually works. When you're talking about real asteroid with real properties, just so we would know if we ever did have to do this for real, and probably never even have to deal with this in our lifetimes, thankfully, but if you have the capability, you want to actually try to do something about it. So this was a chance. Nature kind of gave us this opportunity to do this mission because the idea was it's a lot easier to detect if you have altered the path of an asteroid. If it's a binary asteroid situation, it's a lot easier to see if you've altered the path of one asteroid around another than it is to try to see if you've altered the path of an asteroid going around the sun, especially when we're talking about the small amounts, these test amounts we're talking about. So this asteroid, Didymos, has a moon called Dimorphos, and it was going to be passing plenty far from the Earth, but in a way that you could kind of combine this mission opportunity where the spacecraft is doing the work to go smack the asteroid, and then the observations are done largely from the ground, from telescopes, even though it's just a dot in the sky. You can see how as one asteroid goes around the other, the light from the two of them goes up and down as they pass behind and in front and behind and in front. And what DART was seeking to change was the period of that orbit, or how long it takes to go around there. Could we actually change the speed of one asteroid around the other, change that orbital period, and could we actually measure it? And so this is how it worked out. This is the asteroid Dimorphos orbiting around the larger asteroid Didymos. And many asteroids in the solar system have moons, so this isn't uncommon, but this was very well placed for this mission. It was about a 12-hour period. That's how long it would take for Dimorphos to orbit Didymos. And so DART essentially got in the way of Dimorphos, smashed into it, and then an Italian CubeSat took pictures and flew on by. It was a flyby mission. But that changed the speed of Dimorphos slightly, and so it dropped into this new orbit that had an orbital period of 11 hours and 22 minutes. It was about a half an hour different from its original period, and that was something that was more than measurable from Earth. And so very cost effective, because then you didn't have to have a second spacecraft there. And so this is a really important test of a technique to deflect an asteroid, kind of the simplest technique of them all, just smacking it, the kinetic impactor. And so here's kind of a breakdown of the mission. As what I just showed you, had the DART spacecraft, which impacted the asteroid. There was also a contributed small-sat CubeSat by the Italian Space Agency to take images as it flew by, but it flew by too quickly to be able to do that orbit assessment. That happened in the weeks after impact from telescopes on the ground. And so the launch was on November 24th of 2021, and there was a cruise to the asteroid until finally the impact on September 26th of 2022. And during the weeks afterwards, in fact, it was a lot quicker than they had originally kind of budgeted for. They had that answer of how much the period had changed. But then there was a lot of analysis that took place, and they found the 33-minute change, continued to do analysis, and it's just recently that the project itself has completed. The mission team has done all the work that they were to do for the success of this mission, and now the science community is going to continue to have fun working on the data. Now we're going to relive that. This is sped up, but the approach image from the DART mission is a very simple spacecraft. It's a spacecraft with a camera, and it had one job: hit the asteroid. And it had to not hit the big asteroid, it had to hit the little asteroid. Plus, at the same time, you're getting cool science. We're going to have fun just trying to figure out what we saw even on Didymos. But then, there's a delay between the Earth and the spacecraft. But as you can see, it had no problem doing that final autonomous navigation. And finally, that was the last image where it was sending back image after image, and then finally it got partway through, and then bam. And which sounds really sad, but this was really, really good news. And then to make it a little more, what was it really like? And some of you saw this during the broadcast. Just some bits and pieces from the live broadcast.
I'm starting to see individual boulders on Didymos. Unbelievable clarity of images there.
We're coasting on in. Our projected missed distance is going to be about 17 meters.
Oh my gosh. Oh, wow.
Awaiting visual confirmation.
All right. Let's see. We got it? Waiting.
And we have impact. A giant leap for humanity in the name of planetary defense.
Woo. Fantastic. Oh, fantastic.
Amazing.
What a team. What a team and what an accomplishment.
It's not often that you rejoice when your spacecraft is destroyed. And any of you who might remember the Deep Impact mission, which was a science mission where a spacecraft hit a comet in order to release a plume of material and study what was under the surface of a comet. And that wasn't a deflection mission, it was just to study the properties of the comet. And plus, it was a much bigger object, but to have something as small as Dimorphos, which was about 160 meters in size, and at the speed everything was going, and to actually hit and not miss, this was a really big deal. So that was very cool. Now here's the imagery. You saw a little bit of it earlier from the Italian CubeSat Lucia cube. And you can see Didymos there, and then there's Dimorphos, and you can see the plume of material leaving Dimorphos. And it was just a flyby. DART dropped off the spacecraft, and Lucia Cube continued by after DART impacted. And so even though the measurement of how much did we deflect the asteroid was done from telescopes on the ground, you can't imagine doing something like that and not actually going and seeing it. So it was wonderful to have that contribution, and it adds so much more to the science on asteroid deflection that's coming from the mission. And then also just for looking ahead, a follow-up, the European Space Agency is developing their Hera mission, which will launch to go study the Didymos-Dimorphos system and to really kind of do a detailed analysis of what are the properties of those asteroids, and to study the crater that was left by DART, and to even better refine what actually happened in terms of the deflection, what the physics of the whole deflection process was. You can imagine it depends on the asteroid. You saw it was a pretty rubbly looking asteroid with this plume of material that actually kind of gave an extra oomph to the deflection of the asteroid. But it would be different if you had like a very solid monolithic asteroid deflection, but just the actual event itself. These were the images that came down from, well, not came down, but from the, this is one of our search telescopes that is funded by NASA to look for asteroids, but it made sure it was looking at the Didymos-Dimorphos system at the time of the DART impact. And you can see it's just a point of light. You can't see two asteroids, but boy, you can see that plume of material that came off of there from this small telescope on the ground. This is one of the nicest imagery. And each of these missions does start with the point of light, and so that's going to kind of get back to how does we even know asteroids are out there in the first place? It's great that we had this wonderful mission, but this isn't the only asteroid that's out there. How do we even find them? And so I think my next, here's just a little story about how each of these missions, even the other missions that you've seen in the news to asteroids, they all have to start somewhere. You have to find the asteroid first.
Every mission to a small body starts with a point of light. Spacewatch is a near-Earth object follow-up project of the Lunar and Planetary Laboratory of the University of Arizona, and funded by NASA's Near-Earth Object Observations program. Observing since 1983, Spacewatch began as a discovery survey searching for NEOs. We discovered the asteroid Didymos on April 11, 1996, when Spacewatch team member Joseph L. Montani first observed Didymos as a moving point of light. He proposed the name Didymos after other research found it to be a binary asteroid. The moon of Didymos, Dimorphos, is the target of NASA's Double Asteroid Redirection Test. DART is a test of an asteroid deflection technique for planetary defense, and it all started with a point of light.
All right, so you have to find those points of light, and if Eric and team out here were to show you an asteroid in the telescope there, and if you were to watch long enough, you would see an asteroid moving with respect to the starry background. And so that's part of the challenge. It's kind of like finding a needle in the haystack and then realizing, okay, what's different here? And that you saw an example of that. And so how do we go from, this point of light in the sky and then turning that into an orbit so you actually know where that asteroid has been, where is it going to be in the future? That's what you want to do in planetary defense. Map out the asteroids, figure out where they're going to be in the future, and then find out, are any going to be at the same place at the same time as the Earth? And then sometimes you get cool missions that you can send to them and then see the asteroids close up. So don't let this disturb you. It looks a lot that have made their way into the inner solar system, near-Earth objects and near-Earth asteroids, the asteroids and comets that come into Earth's neighborhood in the inner solar system. But some of them are considered potentially hazardous because they're larger and they come close to Earth's orbit. So we want to pay particular attention to those. And even though this looks so busy, space is still really big. And all of these dots on here, if you were to do this to scale, you wouldn't even see any of this. But the dots are the asteroids, and those are their orbits. And this is good. We know this so far, and we're not worried right now. It's what we don't know about that we're concerned about, which is why let's find the asteroids, let's be empowered, and we might find out, you know what, we're just in monitoring mode. And so that's what we're trying to push to do in NASA's Planetary Defense Coordination Office. NASA has been doing work looking for near-Earth asteroids since the late 90s, but then it got formalized into this Planetary Defense Coordination. Find the asteroids, search, detect, and track. And these are just some of the names of the observatories and such and centers that are involved in that activity, including internationally through the International Asteroid Warning Network. Characterize them, studying their properties of individual asteroids. You want to find out, what are they made of, what are their sizes, their shapes, what can we learn about them. But planning and coordinating, working with the international forums that are set up to engage and collaborate with other countries on planetary defense and the near-Earth object hazard. And then mitigate, meaning, we're empowered, we can do something about it. If we knew about an impact, we could warn, we could work with, in the US, like with FEMA, with other government agencies, or through the State Department with other countries, if we have that kind of information. Or if there's the time, which is the goal, to find asteroids early so that there's the time to actually do something about it with something like the kinetic impactor technique demonstrated by DART or another deflection technique. And then finally assessing, okay, where are we? How do we know what we know? What don't we know yet? How much further do we have to go? And also, just so you know, there is actually a national strategy for planetary defense that defines the role of NASA and other government agencies in this whole endeavor. NASA has a very primary role, but really more with bringing in the information, finding the asteroids, tracking them in the event one is discovered that does pose an impact threat to Earth, doing the determination, the prediction of where it would be, what the effects would be. And so, but that doesn't mean that NASA does everything. And I'm from Hollywood, so I can say this, the Hollywood movies where it's just one lone scientist running around, trying to convince everybody else. No, there's a whole group of people working this, and data are public and everything. And so that is actually laid out in a national strategy that involves NASA and FEMA and Department of Defense and National Science Foundation. Everybody has different roles, and again, hopefully you never even have to do anything about this, but it's there. It's not the first time that we've ever thought of this, which is great. And then NASA has, from that national strategy, detailed specifically in further detail what NASA's role is in this endeavor. And so how are we finding the asteroids? We actually have observatories that we fund around the world through the University of Arizona, the University of Hawaii, and some other organizations that actually do the searching for asteroids. There are telescopes that look at wide swaths of the sky to be able to see that field of stars and to look for those moving objects to see is there something there, and is it a natural object? Is it one we haven't already cataloged? So these are the search projects. The major ones are Catalina Sky Survey of University of Arizona and Pan Stars and Atlas of the University of Hawaii, but also we have a collaboration, I'll go ahead to this slide, with U.S. Space Force and the Royal Australian Air Force, where we fund a team at MIT Lincoln Labs to pull down the natural object data from the images that they're using for other purposes. And there's even a repurposed space telescope called NEOWISE. It was the original Wide Infrared Survey Explorer surveying the sky from space in the infrared, and it wasn't built to be an asteroid detection machine, but it ended up being pretty good at that. And so it was reactivated later on to continue. But I don't know, has anybody here, did you see in the news about the end of mission coming for this? I guess not. Like all good things, it's been in orbit a long time. We're at the height of the solar cycle. The orbit's starting to decay, and plus you have to study the telescope more often. And so we're having to look at when we're going to have to shut down that survey. But, as I'll explain later, there's other activities in the works. And I'll just mention those are the telescopes that are finding the asteroids, plus others around the world that do that work. But then there are a number of observatories involved in getting additional measurements. It doesn't help to just see that dot against the stars unless you have enough information to be able to turn that into an orbit and predict where the asteroid's going to be in the future. Otherwise, it's useless to you. And these observatories and many others study their physical properties. Also, all of the data, so NASA's not the only one doing this, and there are observatories around the world that study small bodies, near-Earth asteroids, but small bodies of any type, main belt asteroids, trans-Neptunian objects. All of those position measurements of those bodies are sent to the Minor Planet Center, which is funded by NASA, but it is the internationally recognized repository for all those small body measurements. And it's public, and so again, anybody can go in and pull these data and do their own orbit determination. And they do the identification, the designation, the initial orbit computation. And again, a lot of these aren't even near-Earth asteroids. They're the holders of all of the small body position measurements. But out here at the Jet Propulsion Laboratory at JPL here in California, the Center for Near-Earth Object Studies, they take those observations and they do high precision orbit determination, both in the short term for something that has been seen one night and it hasn't even been confirmed that it's even like a new asteroid discovery, but just to see, does it pose a short-term impact threat? And then finally, calculating orbits way out into the future, measuring or taking into account rather forces of other objects in the solar system and such to see, okay, could anything pose an impact threat in the future? And the good thing is, even though there's a list of things to keep an eye on, they're all at such low probabilities, there's nothing we're concerned about right now. Again, the bigger goal is let's fill out the catalog so that we know about the ones we don't know. But if ones were found to pose an impact threat, the Center for Near-Earth Object Studies would calculate the time and location and the geometry of that event. Now, we kind of had a situation this last year where and this has happened just a handful of times before. The Earth is pelted by things all the time. I'm sure a number of you here have seen meteor showers, the annual meteor showers, and then sometimes there are small particles or even very, very small meteoroids or small asteroids that hit Earth's atmosphere. And Earth's atmosphere does a great job of protecting us, disintegrating what hits it, and you just end up seeing a shooting star or a fireball or whatnot. And so that happens more often than not. But it's very rare that we actually spot that object before it hits. And this has happened, I think, like 7 or 8 times now. This was Super Bowl Sunday. And I don't know, I'm not a football fan, but Super Bowl, it's like a cultural thing. So I'm there watching TV, and I'm like multitasking, working at the same time. And this alert pops up. And it turns out, the poor guys at JPL, they're trying to deal with the Super Bowl too, and now they're having to deal with this. There was an asteroid that was discovered, and it was predicted it was going to hit Earth in a few hours. And it was only a few hours because this was a very small object. It's about 1 meter in size, barely an asteroid. But this was a wonderful chance to kind of test the whole system. And so even though this posed no threat to Earth, it was just going to make a pretty fireball, this was a chance to test things out. The observations came in from an observatory in Hungary, actually. It went into the Minor Planet Center. The Center for Near-Earth Object Studies pulled the data. They calculated this impact probability, and then they alerted the community and alerted NASA. And so their first calculation, based on the amount of data that they had at first, was that this very small asteroid was going to impact over this region, over Spain, France, or over the ocean. And that's kind of all that was known. But as more observations came in from the observatory there in Hungary, that uncertainty region was narrowed down. Kind of like if you watch like on the weather report, if there's going to be a hurricane hitting, there's that uncertainty cone. You have this region where you know it's going to go somewhere in there, you don't know exactly where, but the more information you get, the more you can narrow it down, until finally about 4 hours before impact, they really nailed that down, and these were the predictions of where this tiny asteroid out in space was going to impact. And you could see this area over northern France. And again, because it was so small, I mean, it was a meter in size, barely an asteroid, so it wasn't something that we needed to warn about or anything in the sense of warning up through the government or whatnot. And it was only found hours before impact because it was so small. It couldn't be seen until it was close. So our goal is to find the asteroids and to find them like years or decades ahead of time, and the ones that could actually do damage. And so this was a great test of planetary defense capabilities, finding, tracking, predicting the impact location. And so NASA and our European Space Agency colleagues, we put it out there on X, on social media, to say, hey, you might get to go see an asteroid impact. And many did see it. And sure enough, here was somebody in northern France there. There it is. Now, how many of you have seen like a fireball like this before? Okay, so a number of you have. I remember seeing one out here in California years ago. It was a star party up on Mount Pino, so it was perfect because we're all up there with telescopes. And then this fireball goes by. We're just like all cheery and everything. So some of you have seen that, but it's very rare that you get a prediction saying, you go out, you look in this direction, you're going to see the fireball. This is a very rare situation, but it was very cool. And I got to see it live because as the Super Bowl's on and I'm sitting there multitasking, and again, data are all public. I'm seeing it all over social media, and people are posting links to webcams. So I was watching a French webcam while I had the Super Bowl on. So if you look up in the upper left corner there, I was just sitting there watching, and sure enough, at the right time, the sky started to brighten. And unfortunately, the camera didn't quite get it, but it just caught where it went by there. So this is what I got to see live. So the whole point is it was an assurance that we can trust the modeling software and such that develops these predictions, that these position measurements in space can be translated into an orbit and into impact predictions. And so, again, a great test, something we'll probably never need, but it's wonderful to at least know that, we've actually done this, and we can be assured about it. Okay, so a few plots. I won't overdo the plots. But you want to know, okay, where are we? Okay, we say we want to keep track of the asteroids, and the smaller they are in size, the more there are. But the smaller they are, the better job our Earth's atmosphere does at taking care of them. So we're not so much concerned about maybe the ones in blue, maybe some of them. There are over 33,000 near-Earth asteroids in the catalog. So that sounds like a lot. And the really large ones in red down there, those are the 1 kilometer and larger near-Earth asteroids. These larger ones, there's far fewer of them. You can see that over the years, things have leveled off. NASA started doing this in '98, found all these big asteroids. Only a couple are found every year. So that population is pretty well taken care of. It's really kind of the in-between size, this 140 meter and larger. It's a size that, should an asteroid that size impact, it could affect a state, or it could affect a country. It could pose a national security risk to the United States or to another country. And so that, even though we're not so concerned with the really large asteroids, impacts are very infrequent. Again, none of these will probably even happen in our lifetime. But it's the sort of thing that if you did know ahead of time, you'd want to be able to prepare. And Dimorphos, the target of the DART mission, that was a 160-meter asteroid. And so that was kind of good to know that, we were able to actually deflect an asteroid of that size. So this is but as you see, that yellow is still going up, so those asteroids are still being found. This plot shows every year how many asteroids were discovered, and you see over time, we're discovering more and more. Those are just the different surveys corresponding to the different colors, the different telescopes that we're doing the searching. And so we've gotten better and better at doing this, although this year, for various reasons, we're going to have a hard time punching through the 3,000 mark like has been done the past couple of years. But these are asteroids of all sizes, all the way down to 1 meter in size. If we look at the 140 meter and larger asteroids, we're finding like around 450 a year. And again, we're having a little tougher time this year. Sometimes there are things that happen, like one of our search telescopes in Hawaii was affected by the Mauna Loa eruption. It just came back online because there's not much you can do when lava takes out the road and the power lines, and so now they're operating fully solar. And then you've got the weather to deal with, like Eric and team is going to have to deal with today. But so sometimes things are different year to year, but you can see that, it's pretty flat. We're finding the same amount every year. And NASA actually has a tasking from Congress that was set up first in 2005 to find the population of 140-meter and larger asteroids to, again, know, okay, that size range, do we have a good handle on them? And it's known as the George E. Brown NEO survey goal. And we're only about 44% of the way there. And with that population that's estimated to be about 25,000 of those asteroids. And at the current rate, what you're seeing up here, it's going to take like another 30 years. Was observing in the infrared, searching the sky, but taking what was learned from that and optimizing it for the search for near-Earth asteroids. And you've heard of the James Webb Space Telescope. It is actually positioned, if you see that L2 point out there, it's positioned at the Sun-Earth L2 point, looking in the sky. And that region away on the right side of the Earth there is what telescopes here on the ground is what they look at. It's night. But the Near-Earth Object Surveyor is going to be positioned at that Sun-Earth L1 point there. You see at that point where it says L1 on the left side of Earth, that's where the telescope is, and those big red cones there, that's the field of regard. It's where the telescope is going to be searching in one cone, searching in the other cone. That's where the survey is going to happen. And that telescope then can look closer to the direction for asteroids. And this, let's see if I have it up here. Okay, I guess I didn't have the launch time, but this is planned to launch no later than June of 2028, and again in development right now, and this will really speed things up in terms of the search. I mentioned it's searching in the infrared because the telescopes on the ground here, they're looking at light that the eye can see. But it can be hard because asteroids, actually even the moon is very dark. It just looks really bright because there's so much sunlight coming off of it. But some asteroids are lighter than others, and this is extreme. But here you've got two asteroids the same size, but except one of them is a lot more brightly colored than the other. And so this one reflects a lot more sunlight than the other. So if you put them way out in space, you can see that, oops, I thought I would be able to pause it. You can see that they look very different. It might even be hard to see that one at all because it's not reflecting a lot of sunlight. And it's hard to get size information when they're, oops, let me back it all the way up here, get this going again. Now I won't mess with it. So if you're looking at light reflected from those asteroids, it might be hard to tell that they're actually the same size asteroids, might be even hard to see one of them at all, but if you could turn on your infrared eyes, if you could see the heat that's being radiated from those asteroids after they absorb radiation from the sun. Let me run that one more time. All right, I'll do it carefully. Here we go. Nope. I think it's not going to let me argue with it anymore. In any case, that's one thing that the Near-Earth Object Surveyor is going to be able to do very well in terms of, here we go. Thank you. In terms of enhancing what can be done from the ground, being able to see asteroids that might be harder to spot from the ground because of asteroid population. Okay, and so this is a simulation of once that telescope turns on, what it's going to find as the Earth orbits the sun, both known and estimated new near-Earth objects, near-Earth asteroids that are 140 meters and larger. So filling in that population very quickly, and so that's going to allow us then to, again, all of these, by the way, NASA's goal is to find asteroids of all sizes, but how do you eat an elephant? One bite at a time. You have to have those goals, and again, this is this congressional goal that's set for NASA to find the asteroids of that size range, but it's going to be very valuable for finding asteroids of all size and telling us, okay, what might have we been missing by using only the telescopes from the ground? So real quick as I get to wrapping this up, again, NASA's not doing all of this. They're actually space agencies and universities and organizations and even some very advanced independent astronomers around the world who are involved in these activities. And there are two UN recommended collaborations. These aren't part of the UN, but UN recommended the formation of this International Asteroid Warning Network, which is a collaboration of space agencies and universities and independent astronomers and institutes who do the observations or the orbit determination. And this is organized by or coordinated by NASA. In fact, one of my other hats is serving as the coordinating officer for the International Asteroid Warning Network. And then its companion group is the Space Mission Planning Advisory Group, and that's a forum for the world space agencies to discuss mission options should an asteroid that threatens Earth ever be discovered. Again, every country, and every space agency ultimately does what it's going to do or what it will collaborate on, but to have this collaborative body recommend mission options will be very valuable, and having these in place just so that, again, it's not like the first time we thought of this if something is ever discovered that poses an impact threat to Earth. And the Space Mission Planning Advisory Group is chaired by the European Space Agency. And then finally, as we wrap things up, kind of in the cool department, there was an asteroid called Apophis that when it was first discovered, because it was a large asteroid, I think it was 340 meters in size, it was at first thought that it was going to impact the Earth, and it turns out it wasn't, which is great. And in fact, recently we had some observing campaigns that ended up kicking it off the risk list altogether. But it's going to make a very close approach in 2029. We know it's not going to impact, but now it's kind of a really cool science target, and it's going. And I showed you an asteroid that impacted, that 1 meter asteroid, and so we have things buzzing the Earth all the time. But to have a very large asteroid approach so close is a very rare event, and it will be approaching closer than the distance of the geosynchronous satellites, like the weather satellites. And it's actually going to be visible with the naked eye as it approaches, but unfortunately it's going to be visible from Europe and Africa and not from here with the naked eye. But that's not to say, Eric was talking to Eric about it earlier. Eric and team are probably going to be all set up here to try to show you Apophis through the telescopes at least, if that all works out, even if it can't be seen with the naked eye here. So that's something really cool that's coming up in 2029. So you might hear about this in the news occasionally. And again, be very discerning when you read these news articles. If you see all this hair on fire stuff about Apophis, it's not even on the risk list anymore, okay? It's just going to be a really cool, close approaching asteroid. Okay, so I have a few QR codes up here, and I'm happy to bring these up again afterwards. But the DART mission did this program where you could answer a few questions about planetary defense, and then you can get a cool certificate. So if you want your Planetary Defender certificate, you can go to this website or use this QR code here to say that you're a planetary defender. I joked about I got to help with the DART launch broadcast, and so we held up our certificates, and I said that when I went in and took the test, I knew what the answer was, but I wanted to make sure that I knew what they thought the answer was. And so I clicked on the little help item, and a video of me popped up. So I guess I should have just trusted myself. And then also, NASA, the NASA History Office has put together a book about the history of near-Earth object research, and this was before the DART mission completed, but it was published I think just 2 years ago, so it's still pretty recent. And I actually brought a couple of coordination office or the DART mission, or this is a kind of a YouTube list of a bunch of short NASA videos about planetary defense and asteroids, if you like that kind of a compilation to kind of get some little bits and pieces about how planetary defense works. And then also very active on social media, NASA social media and NASA solar system. But then we have the NASA Asteroid Watch account on X, formerly known as Twitter, and we don't spam everybody. It's pretty rare that we post, but that will be an avenue where we put out information on hazardous asteroids, or when the news is blowing up about something that we're not even concerned about, then we'll put something out there and say, you know what, it's all good. So these are ways to find out more information also. And so thank you so much for having me. This was really wonderful. I'm happy to take questions, and also when we're all done, do have some NASA and Planetary Defense Coordination Office stickers and lithographs up here that you're welcome to help yourself to. But I'm happy to take questions at this point. Thank you.
Okay. Okay. A couple decades ago, they had a volunteer program where you could link up to the different telescopes and look back at the stars and see where one got lighter and then darker. Do you know what I'm referring to?
Sounds like a variable star?
Yeah, and it was just volunteers that did that.
Yeah, there's the American Variable Star Association.
Yeah, do they still do that? I mean,
I believe so. Is anybody else here involved in that? But yes, there are a number of organizations for doing that kind of, I hate saying amateur astronomy because they tend to be very advanced amateurs, but all of that tends, or we say like citizen science now, and we actually in Planetary Defense Coordination Office fund some citizen science activities. The Catalina Sky Survey has their daily minor planet on Zooniverse, where you can look at images from the asteroid surveys, because sometimes there are things that are missed. There's software that goes and looks for those moving points of light, but it can be a little difficult sometimes. Sometimes there's noise, or it might be a satellite, or something else, or maybe an asteroid that's very faint, and then sometimes you just can't beat the human eye. And so a lot of citizen science projects have helped with finding mainly main belt asteroids, but it helps to get those into the catalog, and then you know what they are. Also, I used to be involved in Jupiter research, and my goodness, the ground-based community, what they are doing with imaging of the planets, they're able to do the monitoring that you can't do with like the large telescopes. They've got so many different things that the community needs from them to do. They can't just sit there and stare at Jupiter. And so what the independent astronomer community is doing for those areas of science, and what's wonderful is that the professional community is including them on their journal publications, because they're contributing. You can do that kind of long-term monitoring that maybe you can't do with individual telescopes, and then other activities like variable stars and such. So there are ways to contribute from the, I say the quote amateur community, because they're very, very, very advanced, and I like saying independent astronomers better.
Question two, now that I have somebody from NASA in front of me, it's always stumped me. Why at night you can look at the sky, you can see the moon all lit up, you can see other planets all lit up, and I know we have things out in the atmosphere, out in the universe, taking pictures of everything. Why don't we ever see a picture of the Earth lit up like a star?
Did you say, why do we not have a picture of that?
Yeah.
Well, actually, there have been pictures like that with some of the deep space probes, like the Voyager missions, when they were way, way, way out.
Really?
In
I'd
the
like
solar
to
system.
see that.
They've turned back, and they've looked, and they've seen, I mean, the term the pale blue dot. I mean, like you said, it almost looks like a star.
So I got to be out there to see it, not nothing.
Yeah, you're not going to see it up close like that. That's what's wonderful. You can see all the detail and everything from orbit. You got to get far away. So,
okay, so that is the what? They took the picture? Voyager?
Like the Voyager missions did
thank
that.
You. Thank
New
you.
Horizons also,
Thank you. It's been driving me crazy.
Okay.
Hi, well, I can't let you go without asking about Neburubu. I don't know if I'm pronouncing that right. Probably the only asteroid that is now almost a household name, next to the one that killed the dinosaurs millions of years ago. And I just want you to talk about, supposedly it was supposed to be interstellar. I don't know. Maybe you could talk more about what you know about it. And it became pretty controversial because of the astrophysicist Avi Loeb, who published a paper on it, believing it had some sort of alien properties or whatever. But can you comment more about that asteroid? Because, it's very interesting.
Okay, I think you're mixing two things up, because Nibiru is something else that isn't, there isn't data on. It's something else that's talked about in other communities. But Oumuamua, I think is what you're talking about. No problem. Yeah, so, no, this was cool. Oumuamua was, when it was actually discovered by the Pan-STARRS telescope, which is funded by NASA. And I remember when that happened, because we heard from the team that we think we found an interstellar asteroid. Because, one asteroid's like another. How do you know? Because again, I said you get enough observations that you can determine an orbit or a trajectory. In calculating that orbit, it was found that, this actually came from outside the solar system. And so that was a very significant thing because it's just a cool science, to study something from another solar system. And by the time it was discovered, it was on its way out, and there was only so much that could be studied, like from Hubble Space Telescope and telescopes on the ground. But so it was it was the first object that was discovered that came from outside. So there have been 2 objects that have entered our solar system that came from another solar system and then passed on through. It gave the science community an opportunity to study something and see, how does it differ from the small bodies in our own solar system, and maybe tell us something about the formation of other solar systems. Mm-hmm.
Yes. What is your motto, your office's motto? What is that? I see it's in Latin.
Oh, yeah. Hic servare diem. It means here to save the day. Now, Star Trek fans out there might know the name Michael Okuda. He's a friend of one of our colleagues, and Michael Okuda kindly designed this Planetary Defense Coordination Office shield for us. And Michael Okuda is one of the graphic designers for Star Trek. And as a big Star Trek fan myself, I can't tell you how cool that is to have had him design that for us. But then our Planetary Defense Officer, Lindley Johnson, who coined the term planetary defense actually many years ago, he always thought it would be great to have Mighty Mouse as a symbol, and that didn't work out, but we can still have the here to save the day on the shield, so it's that combination.
How large is too large an object to change the orbit with current technology like DART? And second part of the question is, where's the technology going to be able to potentiate orbit change?
That's a very good question, because we talked about DART, the kinetic impactor technique, smashing spacecraft into an asteroid, but how large is too large? How large would an asteroid have to be where that wouldn't work? And also, it kind of, in any situation, it would just depend on the asteroid, because we've also heard people talking about we should just have something on the pad ready to go. We might not ever need this in our lifetime or children's lifetimes, but it also depends, and so that would cost a lot for doing nothing, but it depends on the asteroid. It depends on its size, but also its composition. Like I said earlier, is it kind of like a rubbly object like we saw from Dimorphos, or is it a very solid metallic asteroid? What's its orbit? How much time do we have before impact? Because if you have many years, you would only have to deflect it a small amount for it to miss the Earth in the future. But if you didn't have many years, then you might have to deflect it more, and that would take more energy. So all that's to say, the kinetic impactor is one technique, and that really would be more useful for relatively smaller asteroids, because you have to launch the mass to go smack into the asteroid. But there are other techniques. One is called the gravity tractor, where you could put a spacecraft next to an asteroid and just hover there and let nature's tug rope, just like we're all pulling on each other with gravity, just let the spacecraft over a long period of time tug the asteroid, or even like grab a boulder off the asteroid to increase the mass of the spacecraft and hover it there. Ion beam is another one that's being looked at, where you have like an ion engine just firing ions at the asteroid, but you do that continuously for a long period of time. You could tweak it. Hollywood movies, it's always the nuclear option, but you know what? We actually do look at that. We collaborate with the U.S. national labs who do modeling of that sort of thing on asteroid deflection. You don't have to blow up the asteroid. You could use a nuclear device detonating next to an asteroid to irradiate the surface, have the plume that would come off the asteroid like you saw from DART, but from that explosion, would kind of give it the kick in the other direction. So there are a number of techniques, and a lot of them are just looked at with modeling, but hopefully we can test more in the future, like maybe having a mission to test one of these like ion beam or gravity tractor, or do another kinetic impactor test. One of the other priorities for NASA, we have the National Academies of Science. They do every 10 years kind of a survey of planetary science and pointing to what are the priorities in the next 10 years. And for planetary defense, they identified being able to turn around a rapid response characterization mission, a spacecraft mission that could go study an asteroid and learn its properties, because that would really inform, okay, how are we going to deflect it? And if we have many years, which is why we want to discover them. If you have many, many years to plan, then it gives you the luxury of time to maybe send a mission out there to study an asteroid, which would then help you decide if you had to deflect it, how you would do that. So it's kind of a long answer, but really the bottom line is it depends on the asteroid, but a kinetic impactor isn't the only technique that's been considered, and there are other ways to address asteroids of other sizes. And this was getting to test one of them was certainly the first step and gives us a lot more information for assessing other techniques.
All right, I think we're good for one more question.
And I'm happy to stay up here afterwards for those who didn't get to ask.
So I guess I'll just follow up on that a little bit, but how much does it depend in the sense that, like, how confident are we that, so it seemed like from what you were saying that asteroids that are like a kilometer in diameter or larger, we're not that worried about because we kind of know where they are. But ones that are 140 to 1 kilometer, maybe we're worried about it, but in that range, are we pretty confident we could do something about it if we discovered it?
Like DART showed us, like with the smaller end, again with time, the combination of, again, if you find them really early, then you wouldn't have to deflect them as much. You know, if the Earth goes around the sun, the asteroids go around the sun. Ideally, you'd find the asteroid that's a problem many, many times around the sun, both through the Earth and the asteroid, and it gives you different opportunities to maybe do something about it. But all that's to say with, like, as you get to, like, hundreds of meters in size, then it's more challenging for something like a kinetic impactor. So I think that low end is more reasonable there. And even like below 140, that might be, you'd have to do the trades on whether, you know, with the time and what being them, and so they're picked up from orbit. So anyway, point is, as they're larger, then we would have to look at other ways. You could do multiple kinetic impactors. You might not be able to do it with one impactor, but that's why we want to keep studying and learn more, both to have that time, but also to study the different techniques, evaluate them, and see what would you use in what situation. Again, that rubble pile asteroid that we saw there, you know, you might not want to hit it so hard that you break it up into, now you're dealing with all the pieces. So there's more research to be done, but again, having that confidence, we've tried it once, but yeah, it's not, we don't have like the solution for everything, but that was a step along the way. And again, the nice thing is the larger asteroids, there's fewer of them, and so it's really, if something is going to happen, you know, the odds are it's going to be a smaller object, because if it was something really large, we would have found it already, so yeah.
All righty. Thank you again, Dr. Fast.
Thank you.
Dr. Fast is willing to hang out for a few more questions. We again also have our observatory tour starting right now, so if you're interested in going on that, feel free to go right out the side doors.
I think I've...